This YouTube is about the dynamics of going over a speed bump. So imagine that you are in your car, sitting on a scale, the type of scale that registers weight, and you go over a circular speed bump as shown in this sketch here, that has some radius r, concave down, and here you are at the peak of the speed bump going with a linear velocity v at that particular instant of time. And let's imagine that you were going at 10 meters per second, and that we take g to be 10 meters per second, that the radius of the speed bump is 20 meters, and that your mass is 50 kilograms. So if your mass is 50 kilograms and we're assuming that g is equal to 10, that means that your weight is 500 newtons. No contest about that. But the measurement registered on the scale that you're sitting on is less than 500 newtons, and so let's see why. So as usual, a force diagram is a very important tool for thinking about problems like these, and so that's in the upper left-hand corner. That's what I have here. There are two forces acting on M. mg, the downward weight, and then n up, the normal weight, and that's the force of the scale pushing on little m. From uniform circular motion, we know that the acceleration has to be downward towards the center of the circle. So let me label that here because I haven't done that. And so we know the acceleration is this way, and so by Newton's second law, we know that mg has to be longer than n, giving a net force that's in the same direction as this acceleration. So if I do a Newton number 2, as shown here, and I orient my y-axis downward, Newton number 2 in the y direction, I would get mg minus n is equal to m times a. But since it's uniform circular motion, I know that a is v squared over r. And so I can now solve for n, the normal force, and with a little bit of algebra, n is equal to mg minus m times v squared over r, factoring out the m times the quantity of g minus v squared over r. So let's put some numbers in. 50 kilograms times 10 meters per second, this is g, minus 10 meters per second, that's the linear speed, squared divided by 20. This is 100. 100 divided by 20 is 5. And so inside the parentheses, you have 10 meters per second minus 5 meters per second, which gives you 5 meters per second, which means the reading on the scale is 250 newtons, half of your weight. So we know that that n is equal to 250 newtons, but now we know from Newton number 3, so let me put that in here, Newton number 3, that the force of m on s, which is the force of u on the scale, that's what causes the scale to register a reading, is equal to the negative of the force of the scale on m. Well, this is, of course, this quantity right here is equal to n, as you can see from the picture up here. And so the magnitude of this force is 250 newtons, and since it's the negative of the normal force, which is pointing this way, it's pointing down, and that's your force on the scale. So this situation is known as your apparent weight being half your normal weight. Your weight doesn't change, the force with which the Earth pulls on you doesn't change, but the scale reading if you're standing or sitting on a scale, the scale reading changes. So you might ask whether it's possible to have uniform circular motion in such a way that your apparent weight increased. And that indeed can happen. That indeed can happen, and the way in which that would happen would be that instead of having a circle that's concave down, you could have a circle that was concave up. So in other words, if you were going like this instead, then this acceleration would be pointing up, n would be bigger than mg, and your apparent weight would be bigger than your normal weight.